Hi, my name is Lena Cibulski, and I would like to share with you a novel parallel coordinates technique that we developed to make decisions where choices affect each other. This research undertaking has its roots in a prior design study on the design of customized electric motors. Back then, during the evaluation, it turned out that what the engineers actually need to decide upon are typically not single motors, but multiple interacting mechatronic components. So we turned towards the problem of making codependent choices, and we came up with composite parallel coordinates to enable engineers to also take into account the mutual effects of choosing multiple components. Our starting point is the task of making a so-called multi-attribute choice. Identifying the most preferred solution among a number of alternatives is a common task in our everyday and professional lives. Think of your last holiday stay, for example, where you needed to choose a hotel, or think of the engineers who need to decide which motor design out of many should be taken to production. The common ground here is that each option is valid in its own way, and we need to trade off different properties to come to a conclusion. This requires human judgment. Now, what exactly is it that makes choices difficult? First of all, choices most often concern an ill-defined problem, where the ideal solution is hard to articulate. So to not overlook a solution, we usually compile ourselves large sets of options to choose from. Computing has made this very easy, even if options come with many properties. The actual choice then involves conflicting goals, but is also shaped by the experience and domain knowledge of the individual who's making that choice. To summarize, it relies on highly subjective preferences, which might even shift as we learn what level of performance is achievable under which conditions. However, it can get even more difficult. With multiple interacting components, the task turns into a series of codependent choices, one for each component. And each choice needs to consider the side effects on the entire system's operability and performance. Making trade-offs thus extends beyond one single component. As an example, let's consider a motor that needs at least a gear to transmit the generated power to where it's needed. So, deciding for a motor design rules out gear variants due to missing interoperability. And the superiority of a motor design depends on its interplay with the gear. Thus, the performance can only be judged with both items together. These mutual dependencies significantly intensify the decision-making process. Let's dive a little deeper into this example. In the magnetic geared motor, motor and gear are arranged next to each other within a common housing. They share a high-speed rotor, which means that the outer diameters for this rotor should be the same. Another dependent design parameter is the gear ratio between the shared high-speed rotor and the output rotor in the gear. And as a representation of the overall performance, as motor and gear are arranged side by side, we can approximate the construction volume by simply adding up their lengths. Before, this kind of codependent choices was approached in an iterative manner. So you start with one component, choose the most preferred variant of it, then use its properties for the choice of the next component. That means to check for interoperability and the joint performance. Then you might realize that you cannot achieve your desired optimization goals, so you go back to the first component and choose the next preferred variant, then repeat the remaining choices. All in all, a tedious and at times frustrating trial and error process. We introduce a novel variant of parallel coordinates for the visualization of codependent choice options. We made parallel coordinates the basis of our visualization design, primarily for their lossless mapping and flexible axis arrangements, but also for their simple applicability and widespread use in multivariate data exploration. Codependent choices require analysts to investigate individual component properties, but also emergent overall properties. This leads us to 4 visualization design goals. First, a visualization design needs to allow decision makers to focus on the individual properties of one component at a time. At the same time, a visualization needs to account for the fact that intermediate choices are building blocks of a larger decision. This requires to connect observed component properties to semantically related properties of other components. Third, the success of an intermediate choice builds upon an evaluation of the overall decision quality. The evaluation of interoperability and emergent performance requires an observation of related attributes across components. After all, these three goals are conflicting because each of them requires different access of a parallel coordinates visualization to be rendered spatially close to each other. Underlying these three goals, the fourth design goal addresses the layout stability. It is about avoiding the axis order to be constantly adjusted to a varying analysis focus. In contrast to open data exploration scenarios, codependent choices rely on a clear mental model of the dependencies and attributes to investigate. A stable overview layout allows analysts to focus on trade-offs instead of adapting to varying layouts. To summarize, our visualization design was guided by the question how to make component properties, their context, and system properties equally accessible in a stable layout. We developed composite parallel coordinates, whose axis layout and interaction patterns reflect the notion of a decision being a composition of codependent choices. We place multiple parallel coordinates plots on top of each other, one plot for each component involved. This is to be able to analyze variants of individual components on their own, just like before. The special thing is that those attributes that are semantically related across components, like the outer diameters or lengths, are placed in one vertical line. And then, to analyze the joint performance of both components, these attributes can be collapsed into so-called composite axes. These composite axes can depict interoperability, for example, do the components have the same outer diameter? Or they can depict joint performance indicators, like the total length of motor and gear together. Unlike any other layout that we considered, this strategy addresses all four design goals. That is, it solves the component level analysis with context awareness and the system level analysis while providing a stable layout. Now, what does that look like in the visualization? Here we have gear variance in purple and motor variance in green. In the center, we see the shared design parameters rotor diameter and gear ratio. Next to them, to the right, we see a composite axis that depicts the total lengths of combined motor and gear variance. Next to that collapsed axis, we can see an axis pair with a small plus sign in between, meaning that the individual losses might be merged via addition to view the total losses of the system. While composite parallel coordinates readily allow for an overview of all codependent alternatives, interaction is essential for their effective use. It allows analysts to eliminate undesired alternatives and highlight alternatives of interest. Our interaction mechanism involves three cascading selectors to gradually refine a selection of alternatives. The selectors are hierarchically structured. Filters take precedence over locks, which in turn have priority over mouse-over interactions. Each selector operates on the outcome of the precedent selector. At any time, the selection resulting from the current cascade of active selectors is highlighted, while the remaining alternatives are depicted in gray for context. Let's take a look at an exemplary workflow. Filtering basically works in a standard way. It uses composite brushes that can be applied to any axis. However, the combinatorial nature of the codependent choices gives rise to some special considerations. Most significantly, a component variant is not only selected if brushed itself, but also if it can be combined with at least one brushed variant of another component. Users now need support in scanning through the remaining acceptable options to further refine the selection. Due to the combinatorial nature, multiple combinations might pass through the same polyline segment, in particular where collapsed axes are adjacent. An interaction with a polyline segment can thus lead to more than one combination being hit. For example, let us hover all motor gear combinations with a diameter of 24 and a gear ratio of 22. This mouse-over selection is temporary and falls back to the superset of filtered alternatives once the cursor leaves the segment. So for further drill down, we need to lock it first by clicking the polyline segment, which permanently updates the selection to the respective subset of alternatives. Anything that remains in the selection after applying the cascade of filters, locks, and mouse-over is highlighted. At the end of an analysis, this is usually a unique combination of component variants, that is, the final system choice. Now let's observe the actual use of these interaction patterns in a short live demo. So the primary objective is to minimize the power loss of the entire system. So first we need to merge the losses of both components by adding them up. And now here with the shared design parameters, we can see the different configurations of the system, so combinations of diameter and gear ratio. So if we hover through them and observe the total losses, we can see, well, here the range is covered. And here we have a rather smaller cluster, narrow cluster of system variants resulting in rather mid-range losses, which is quite special. But now we will go back to the total losses and apply a constraint. So we will simply restrict the losses and see what happens. So if you observe the separate pathways, which depict the individual component properties, we can see that there was not that much of an influence, so we can still choose among the entire ranges of individual properties. And then the second objective is to minimize the construction volume. And I already said we can approximate the construction volume by adding up the individual lengths. However, to filter for that, it is more meaningful to do that at the component level, because otherwise we could not identify combinations where the total length itself is acceptable, but the individual motor and gear lengths differ significantly, which is not desired. So we do that at the component level and restrict the lengths for each component on its own. And again, see what happened. What is now striking is that here, this entire cluster of gear variants, because it's a purple axis, gear variants with low magnetic flux density, which is desired, have been removed from the selection. So we might ask, where did that come from? How did that happen? So if I try to loosen this restriction on the overall losses, then we can see that slowly these variants move back into the selection. And then we could say, well, okay, let's investigate this correlation from the inverse perspective. So let's just filter for low magnetic flux density. And what we can see here now is that the system variants with low total losses have been, again, excluded. So what we have here is a relationship or a conflict between a component level criterion, so the magnetic flux density of the gear, and a system level criterion, so the total losses which were added up. Now, what we can also see is that for the configurations, we have one combination here with higher rotor diameter, but as you can see on the axis of the total losses, it results in rather high losses, at least highest losses from the selection. So this one might not be that desired. So we might conclude that this configuration with a rotor diameter of 21 and a gear ratio of 18 might be superior, might be from these four configurations, the superior configurations. And this is also what the engineers found and also reported in their publication. So we would like to continue with this selection. So I would lock it by clicking on the polyline section. to be able to interact with the remaining polyline sections, because once I move the mouse from this polyline section, the selection will be gone. So I need to lock it. And now what we can see here is one outlier in the motor length, which actually results in the lowest losses from the remaining selection. So I hope you can see that when I move back and forth. So what we might conclude is that this motor variant might be our motor design option of choice. And the only question remaining is with which of these remaining gear variants it should be combined. But that's for another day. A distinctive contribution of our technique is the possibility to jointly explore the variants of multiple components and their combinations. Up to now, composite axes represent only one-to-one mappings, involving fairly simple predicates and mathematical operations. Where further non-trivial compositions are required, a more flexible representation of composite axes is needed. We have demonstrated the working principle for two components, but an obvious limitation of the composite layout is that it does not effortlessly scale to an arbitrary number of components. While the vertical layout in principle allows for stacking more than two components, any component could only be directly connected to its two neighbors above and below. Future layout and interaction considerations thus need to address the relations between non-adjacent components, the branching of polylines, and also navigation. Our usage scenarios and case study demonstrated that our technique does in fact support the identified analysis tasks for making a codependent choice. Still, we need to investigate the trade-off between visual complexity and usefulness in more detail. I would like to conclude with the following take-home message. For the first time, our composite parallel coordinates design allowed decision makers to work through a series of codependent choices simultaneously and directly take into account the effect of each intermediate choice on the overall decision quality. There's a lot more insights in our paper, so if you got interested, I kindly encourage you to go for a reading. And with this, I would like to thank you very much for your interest and time.